In this video, we're going to do derivatives of exponential and logarithmic functions. And before we do that, we're just going to refresh some knowledge about exponential and logarithmic functions that you would have learned in your Algebra 2 class in high school, college algebra, or your pre-calculus class in college. Depends on where you had the knowledge and may have forgot the knowledge. So we're going to take a few moments to just remind ourselves about logarithmic and exponential functions. So y is equal to base. This is the base. It is not a variable, it is a number. We'll call it base e to the x. So y is equal to e to the x. And you'll notice that x is in the exponent. The variable is in the exponent, so we know that this is an exponential function. The inverse of e to the x is the natural log of x, which is log based e of x, but we use ln. Here's a graph of e to the x. Here's the graph of the inverse. And if you recall from your previous knowledge that the function and its inverse will be reflected over the line y is equal to x. Some previous knowledge information, just bringing it forward again, is that e raised to the natural log of x is equal to x all day long for x greater than 0. And the natural log of e to the x is equal to x for all x. Now, this is for e to the x and the natural log of x. This will work for base b to the x and the log based b of x. And then, of course, we know that y is equal to the natural log of x if and only if x is equal to e to the y. And, of course, this is true for b to the x, which is equal to e to the natural log of b to the x, which is e x b to the x. Now, what came in here is some log rules. So I would recommend, if it's been a while since you've had logarithmic functions, that you go refresh some of the log rules. One of the log rules that we'll use is the product rule. So log based b of m multiplied by n is the log based b of m plus the log based b of n. Another one that you may need to know and refresh, the log base b of m divided by n. This is the quotient rule, which is the log base b of m minus the log based b of n. And then the last one, if you have the log based b of m raised to the p power, then this p comes down out front as a multiplier on the log. So this is the rule that we used right here. That's why that x is in front of the log of b. Okay, so here is what we have as our definition of the derivative. Well, not definition, our theorem of the derivative of the natural log exponent. If we have this function e of x is equal to e raised to the x, then its derivative is e to the x. Now here's where the chain rule comes into place. If I have the derivative of e to some function of an x, then it's going to be e raised to that function multiplied by the derivative of that function. You might see it in terms of u, so d du of e to the u is equal to the e to the u prime. Either one of them is fine to use on your note card. Of course, you don't get a note card for the test, but as you are practicing and preparing for tests and quizzes, that you might want to have a note card, flashcard with these derivatives on them so that you get used to finding the derivatives. Okay, now here we're asked to find the derivatives of each one of the functions. We're not asked for multiple derivatives. We're not asked for higher order derivatives. We just want derivatives. So I'm going to take the derivative of my first function, which is just going to be the derivative of x is just 1. And the derivative of e to the x is e to the x all day long. We love that. For my next function f prime of x, I'm going to use the power rule. So I'm going to do 7 multiplied by 5, which is 35x. Losing a power, dropping a power, subtracting a power. So it'll be x to the 6. And then minus 3e to the x, because e to the x is e to the x all day long, and 3 is just a multiplier. And then the last one, pay attention that this is a constant, so its derivative would be 0. If we take a look at our next function, g prime of x, is going to be 3 over 2 multiplied by 1, because that's the derivative of x, plus 7e raised to the x, because the derivative of e to the x is e to the x all day long, and then it'll be plus 3x raised to the negative 4, because that is the power rule. Now, none of these are really kind of interesting until we get to D. With D, we get to add the chain rule. So D is going to be r prime of x is going to be 3 the cosine squared of e to the 2x. And that's because what we have is a composition of functions. So our outer function, so if I want to write r of x, is going to be a composition of functions. Our outer function, which I'm going to call h of x, is going to be the cosine, or actually it's not even cosine, it is the x squared. So that'd be the x cubed. Apologies, x cubed. So then the next function in, which would be my f of x, would be the cosine of x. My next function in would be g of x, which would be e to the x. And then my most inner function, which I'll call m, I guess, m of x, would be equal to 2x. So r of x is going to be h of f of g of, g needs to be in black, of m of x. So you're like, what just happened? So its derivative, r prime of x, needs to be the derivative of h evaluated at the inner function, so f of g of m of x. Getting all my colors in here correctly. I know there's a lot going on. Then it would be multiplied by f prime evaluated at g of m of x. Then that gets multiplied by g prime evaluated at m of x. And then that gets multiplied by m prime of x. All right, so let me go back and let me do this in color so you can see what I'm doing when I'm doing r prime. So r prime is going to be the derivative of the most outer function, which would be the cubed function. So that's why there's a 3 here. And if you want, I can write this as the cosine and then have the squared on the outside instead of cosine squared. Now my inner function then would be the cosine, and then inside of that would be, let me do that in green, the colors one says. So it'd be the cosine, it would be e raised to the 2x, and I need my green again. Now I'm going to do the derivative of cosine, which is going to be negative sine. This is a multiplier. And then I'm going to have e raised to the 2x. And then the derivative of e is going to just be e raised to the 2x. And then I do the derivative of 2x, which is just 2. Wow, that's a lot of colors. Now let me just clean this up. So I'm going to erase all of this. And you can see what I did was I did the derivative starting with the most outer function, working my way in. And the way I would have done this quickly is I would have said this is 3 the cosine squared of e to the 2x multiplied by a negative. That's why I'm going to put a negative out front. The sine of e to the 2x, and then multiplied by e to the 2x multiplied by 2. So I would write this as negative 6e to the 2x, the cosine of e to the 2x multiplied by the sine of e to the 2x. And there it is in all of its glory. All right, now we're going to start talking about doing the derivatives of the natural log. Because the domain of the natural log, or any log for that matter, base b, is 0 to infinity, where 0 is not inclusive, then we need to consider the absolute value of x, which is defined for everything except for 0. So if we say the natural log of the absolute value of x is the natural log of x, if x is greater than 0, and the natural log of negative x if x is less than 0. Then, for x greater than 0, the derivative of the natural log of the absolute value of x is 1 over x. And if for x less than 0, then it's going to be the derivative of the natural log of negative x, which is 1 divided by negative x multiplied by negative 1, which is 1 over x. So basically, here's the gist. The derivative of the natural log of x is going to be 1 over x. So here is the next theorem. The derivative of the natural log of x for x greater than 0 is 1 over x. If we have the natural log of a function in terms of x, it will be 1 over the function multiplied by the derivative of the function. Now you might also see this as du. The natural log of u is equal to 1 over u multiplied by u prime. Either one of them. Again, flashcards to make sure that you know what how we define this, and also so that you can practice it. Have that card in front of you as you are practicing. All right, so in general, for x not equal to 0, we are going to say the derivative of the natural log of the absolute value of x is 1 over x, and then of course, by the chain rule, this is what we have. So if we're asked to find the derivative of any of these, we'll start with the first one. This is going to be the 1 over this function and then the derivative of that function. So this would be u would be 3x. And so du of the natural log of u is 1 over u and then u prime. So in this case, dx of the natural log of 3x is going to be 1 over 3x multiplied by 3, which is still just 1 over x. So that's kind of nice. If we take a look at b, our u would be 2x to the 8th. So this du would be 1 over 2x to the 8th multiplied by that derivative, which is going to give me 16x raised to the 7th power. And you will notice here that the 16 and the 2 cancel, giving me 8. And the x's cancel, so I have 8 over x. That's kind of nice, huh? If we take a look at our next derivative, this is the product rule, because what's going on here is a multiplication. So I'm going to do the derivative of my first factor, so that derivative of that, which is just going to be 2x, multiplied by my second factor, which is the natural log of x cubed. And then it's going to be plus the derivative of my second factor, which is 1 over x cubed multiplied by 3x squared. And then that's going to be multiplied by my first term, my first factor, which is x squared plus 1. Now, this then is going to clean up just a little bit. And so I'm going to end up with 2x, the natural log of x cubed. The x cubed is belonged by the natural log, so that x cubed is not going to multiply by the 2x. That is a factor in front. However, on my next grouping, you will see that these will cancel down to just x. So I'm going to have 3 over x multiplied by x squared plus 1. And of course, I can multiply that 3 over x through that x squared plus 1, but it's not going to really do much for me, so I'm going to leave it as it is. If I take a look at d, this is the chain rule. My inner function u is the cosine cubed of x, which means I still have another function inside of that because it's not just cosine, it's cosine cubed. So this derivative is going to be 1 over the cosine cubed of x multiplied by the derivative of the cubed function, which would be 3 the cosine squared of x, and then multiplied by the derivative of cosine, which is negative sine of x. Now this does clean up a little bit, so the cosine squared and the cosine cubed will cancel down to a cosine of a power of 1. And then I have a negative sine over cosine, so this ends up becoming negative 3 the tangent of x. On E, I have a either quotient rule or a product rule, and I'm more inclined to rewrite this as a product rule. So I can write this as x raised to the negative 3, the natural log of x squared, because I like the product rule better than the quotient rule. So this derivative would be equal to negative 3x raised to the negative 4, the natural log of x squared. And then it's going to be plus 1 over x squared multiplied by 2x. That's the derivative of the natural log of 2x. Multiplied by x raised to the negative 3. This will end up becoming negative 3, the natural log of x squared, all over x to the 4th. This cleans up so that this x and one of these cancel. So I'm going to have also plus 2 over x to the 4th. And since these have common denominators, I can write this as 3, the natural log of x squared plus 2 all over x to the 4th. All right, now what we focused in on up until this point was the natural log and base e for both the natural log and for the exponential. But life is not about just base e, it's also about base b. So how do we get to those? Well, the derivative of any exponential function, so for the base b instead of e, the derivative for any any base b is going to be base b, the natural log of b. So here is the equation of y equals 2x. And then, of course, when we go to do its derivative, it would be e to the 2x, the natural log of b. So that brings us to when we have the log base b of x. Here's its derivative. We have the log base b of g of x. Here's its derivative. Notice how it's 1 over g of x, natural log of b, multiplied by the derivative of the g of x. So if you want to use u on your note card, so if you have d and du of the log base b of u is going to be equal to u prime over u, the natural log of b. And then we talked a little bit about this one. If you have the b raised to some function of x, not just x, so you could say d du of b raised to the u is going to be b raised to the u multiplied by u prime multiplied by the natural log of b. Again, make sure that you have these handy as you are practicing, and the more you practice, the better you are going to get at these. Let's do some examples down here. If I'm asked to find y, the derivative of y is equal to 2 to the x, dy dx, or y prime if you prefer, is going to be equal to 2 to the x, the natural log of 2. I don't have to multiply by the derivative of x because the derivative of x is 1, so I guess I kind of am multiplying by the derivative of x. If we take a look at b, I have a product rule I have to do, so I'm going to have y prime is going to be equal to negative 4 raised to the negative x. And the reason this is negative 4 raised to the negative x, because if I follow the same rule, I have my b raised to the negative x, but the derivative of negative x is negative 1, multiplied by the sine of x, and then plus, I'm now going to do the derivative of sine, which is the cosine of x. And then this is going to be multiplied by 4 raised to the negative x. If we look at c, I have p. This is p prime of t. So it'd be p, the derivative of p with respect to time, is going to be equal to, well, this 40, if I write this as 40 multiplied by 1 plus 2 raised to the negative t raised to the negative 1, this 40 is just a multiplier. And then I can use the chain rule and avoid the quotient rule. So this will be multiplied by negative 1, and then 1 plus 2 raised to the negative t raised to the negative 2. That's the derivative of the outer function, which is t raised to the negative 1. Now I'm going to do the derivative of the inner function, and the inner function piece that is not going to be 0 is the 2 raised to the negative t. So this will be multiplied by, negative 2 raised to the negative t, the natural log of 2. And that is the derivative of 40 divided by 1 plus 2 raised to the negative t. Now, If I rewrite this using my rules, this is just x multiplied by the natural log of 10. Natural log of 10 is just a number. And so y prime on this one, y prime is just going to be simply the natural log of 10 because we know the derivative of x is 1. So that was kind of nice. All right, so on E, it is base 10. If I don't see anything besides the log, I don't see log 7, log base 2, it is base 10. And I notice that I have the secant. Well, the secant is a function, so this is a function within a function, and so I know that f prime of x is going to be equal to the derivative of secant, which is secant tangent. So the secant tangent of x, that's the derivative of secant, and then it's going to be divided by u, which is the secant of x, and then it's going to be multiplied by the natural log of my base, which is 10. Now you can see my secants cancel, and so I end up with the tangent of x divided by the natural log of 10. Now let's look at f. So f has a function within a function. The outer function would be x to the 5th. The outer function would be x to the 5th. The inner function is 6x to the 4th plus 3, and so we have a function within a function. So f prime of x, this is the derivative of the inner function, which is going to be 5, 6x to the 4th plus 3 raised to the 4th power. And then I have to go inside further and do its derivative, so that'd be 24x to the 3rd. And then it's going to be divided by my 6x to the 4th plus 3 raised to the 5th power, because that is my u, and then it's going to be multiplied by the natural log of 7. And of course this will cancel down, so you would do some cancellations here, that one of these would, 4 of those will cancel to one of those, and we'd end up with 5 multiplied by 24, which is 100 and, let me see, is that 120? 120x to the 3rd over 6x to the 4th plus 3 multiplied by the natural log of 7. All right, so this last one, I have a product rule going on. And not only do I have a product rule going on, I also have this x squared minus 4. So I'm going to write this as f of x is equal to 2 to the x. I'm going to bring this exponent down out front, so that's going to be x squared minus 4, the log base 3 of 7. And that allows me to treat the log base 3 of 7 as just a constant. And so there's a multiplication going on with just that. So f prime of x, the derivative of 2x is 2 to the x, the natural log of 2. And then multiplied by x squared minus 4, multiplied by this constant, which is the natural log of the log base 3 of 7. And then plus, now I'm going to do the derivative of x squared minus 4, so that's going to be 2x, multiplied by 2 to the x, multiplied by the natural log, or the log, I don't know why I keep on doing natural log base 3 of 7. This will clean up just a little bit, but not enough to really clean up of interest. This I just want to talk about a little bit. This is 2 to the 1 multiplied by x multiplied by 2 to the x. Now the 2 has the same base, so I could write this as 2 to the x plus 1 and then multiplied by x if I was inclined. May be worthwhile, may not be worthwhile. So, yeah, meh. Sometime, well, Calc 2 it'll be worthwhile, but right now, meh, it's okay. All right. Sometimes you're going to have functions in which you have a function raised to a function. When this happens, what we're going to want to do is we're going to want to rewrite this, because we know that b to the x is e raised to the x, the natural log of b, is we're going to write the f of x, which is a function raised to the function, as e raised to the outer function, the natural log of the inner function, or the base. Let me say that again. This is the base, and so it'll be the natural log of that base function. This is the power function, the function that is in the power position. It's not a power function, but it's the power in the function. So notice that when we rewrite it in e, it is e raised to the function that was in the power position, the natural log of the base function. Cool. Then, by the chain rule, we're going to get the derivative of g to the x raised to the h of the x is going to be e raised to hx natural log of gx multiplied by, because this is the chain rule, it's expanding on e raised to a function, h prime multiplied by natural log of g plus 1 over g of x, the derivative of g of x multiplied by h of x. Whew. Wow. Okay, so here we want to find the derivative of each function and then evaluate the derivative at the given value of a. So, all right, we're going to use this. Again, I'd probably write that down somewhere till you get some practice. And we're going to do the derivative of g of x, and then we're going to evaluate it. And I think we really want to have the given value of x. A given value of x, not a. So we're going to evaluate these at these given x values. All right, so the first thing we have to do is take the derivative. And so g prime of x is going to be equal to e raised to my exponent function, which is the natural log of x, multiplied by the natural log of my base function, which is x. This then is going to be multiplied by my exponent function, which was the natural log of x in this case. So it's going to be 1 over x. The natural log of my base function, in this case happens to be x. And then plus 1 over, well, my base function, g, in this case is 1, so it'd be 1 over 1. And then the derivative of x is just 1, so that's all going to be x. And then multiplied by my power, the function that's in my power, in this case happens to be the natural log of x. All right. So now what we're going to do is we're going to evaluate this at x is equal to e. So then g prime of e is going to be e, the natural log of e, multiplied by 1 over e, the natural log of e, plus the natural log of e. Again, you'll probably want to open up your pre-calculus book. OpenStax has a really nice pre-calculus book, or some other place to find the rules. And when we have the natural log of e, that is just 1. So this is going to be 1 multiplied by 1. So this is going to be e raised to the 1 multiplied by 1. And then I have 1 over e multiplied by 1 plus 1. So this is all going to be equal to e multiplied by 1 over e plus 1, which just gives me 1 plus e. And that is my final answer. Wow, that was a lot. All right, let's take a look at my next example here. And so on my next example, again, I'm going to decide what is my power, what's the function that's in my power position, and what is my base function. So this is my h of x. I'm going to label this my g of x. So then f prime of x is going to be equal to e raised to the g of x, which is going to be, the h of x, which is just going to be x. So this is going to be x, multiplied by the natural log of my g of x, which is x squared plus 1. Then this gets multiplied by the derivative of my h of x, which is just x, so the derivative is 1, multiplied by the natural log of x squared plus 1. And then plus 1 over my g of x, which is 1 over my x squared plus 1, multiplied by my derivative of g of x, which is 2x, and then this gets multiplied by my h, which happens to be just x. All right, so now I'm going to evaluate this when x is 1. So when x is 1, I'm going to have e raised to the 1, the natural log, oh, sorry, that should be as an exponent. The natural log of 1 plus 1 multiplied by the natural log of 1 plus 1 plus 1 over 1 plus 1 multiplied by 2 multiplied by 1. So this is going to be e, the natural log of 2 multiplied by the natural log of 2 plus 2. But e raised to the natural log of any value is that value. So this is just going to be 2, the natural log of 2 plus 2. So I have 2, the natural log of 2 plus 4. And that's my final answer. All right, so let's take a look at my last example. So what I'm going to do is I'm going to go ahead and erase this. Let me erase this. So I'm going to erase all of this so I have the space again. Okay, so we're now going to do the h of x is equal to the tangent. So once again, I'm going to label what I have. This is f of x, and this is g of x, or I guess it was h of x. So let me erase that. So that's h of x. That's h of x. So, oh, I'll make this f of x. So f prime of x is going to be equal to e raised to the x minus 1 multiplied by the natural log of the tangent of x multiplied by, so if you remember, it would be multiplied by, it is the derivative of h, so that's just 1. So multiplied by 1, the natural log of the tangent of x plus the derivative of, so it's 1 over the tangent, so I have 1 over the tangent of x. I should do that in red. Let me put that back in red. 1 over the tangent of x. The derivative of the tangent is the secant squared of x multiplied by x minus 1, which is my h of x. Now I'm ready to evaluate this, and so I'm going to have e raised to the pi over 4 minus 1, the natural log of the tangent of pi over 4, multiplied by 1 times the natural log of the tangent of pi over 4, plus 1 over the tangent of pi over 4, the secant squared of pi over 4, multiplied by pi over 4 minus 1. The tangent of pi over 4 is equal to 1. The natural log of 1 is equal to 0. So that's kind of nice. So then this whole thing becomes e raised to the 0. E raised to the 0. This also becomes 0. Now, so I have e raised to the 0 multiplied by 0 plus the tangent of pi over 4 is 1 over 1. Secant, well, the secant of pi over 4 is the square root of 2. So if I square the secant, I'm going to square the square root. And so I'm going to have secant squared is just going to be 2. So that's going to be multiplied by 2, multiplied by pi minus 1, pi over 4 minus 1, excuse me. E to the 0 is just 1. So this is just going to be 2 multiplied by pi over 4 minus 1, and I can either leave it like that or I can distribute, and that is my final answer. All right. So here are the properties of logs. I did give you a couple in the beginning of the video, but you probably want to write these down somewhere so that you can have them. here are some strategies to do logarithmic differentiation. Now, why would we want to do logarithmic differentiation? Well, the reason we'd want to do this is if the thing I'm trying to take a derivative of is awful. So if I take a look at A, it's not too bad. I probably wouldn't do logarithmic differentiation. Problem B, I may or may not do logarithmic differentiation. C, I probably would. What is logarithmic differentiation? Well, basically it says, I'm going to replace f of x with y. So I'm going to write this as y is equal to x squared, the cosine of x. And then what I'm going to do is I'm going to take the natural log of both sides. Well, why the natural log? Because the natural log is the easier one for derivatives because it's 1 over u prime. So when I do that, I'm going to get the natural log of y. The natural log of y is equal to the natural log of x squared multiplied by the cosine of x. Now I can use the log rules to write this as the natural log of x squared plus the natural log of the cosine of x. Well, the natural log of x squared becomes 2, the natural log of x plus the natural log of cosine of x. Again, I probably would not do the natural log on this first one. I would just use the product rule, but I'll show you how this will work. Now, once I have the fact that the natural log of y is equal to this, I can use the way that I do differentiation for the natural log. Because I have the natural log, which is a function, so its derivative is going to be 1 over y, and then dy dx, because it is a function. Y is defined as a function of x, so it's dy dx. And then this is going to be equal to 2 multiplied by 1 over x, and then plus 1 over the cosine of x, negative sine of x. And so I end up with dy dx, 1 over y, is equal to 2 over x, and this is the negative tangent of x. But I need to solve for dy dx, so I need to multiply both sides by y. So dy dx is going to be y multiplied by 2 over x minus the tangent of x. Now, y was x squared cosine x. So this is going to be x squared cosine of x multiplied by 2 over x minus the tangent of x. If I distribute this x squared cosine of x, I'm going to get 2x minus, I'm going to have tangent multiplied by the cosine, which is negative sine of x. Again, I would not have taken the natural log of both sides and then done its derivative, right? Because that's a whole lot of work to come back up here and say, oh, I'm just going to use the product rule. And if I use the product rule, f prime of x would be equal to the derivative of the first one, which is 2x, the cosine of x, plus the derivative of the second one, which is negative sine of x multiplied by x squared. Which, had I multiplied correctly, I would have had an x squared there. Now, I would not have done the natural log of both sides. To me, that's just a waste of time and brain space. So what would I've done? I would have used the one that was the most appropriate, which would have just simply have been using the product rule. Same thing with B. It is unlikely I would use the logarithmic differentiation, but on C I would. So I'll let you look at B, and I'm just going to focus in on C. Now C, I'm going to rewrite this as y is equal to x to the 8th, the cosine cubed of x, divided by the square root of x squared minus 1. So then the natural log of y is equal to, now when I take the natural log of the right-hand side, I'm also going to simultaneously, to save myself time and energy, I'm going to use the laws of logs to expand this out. So this will be 8, the natural log of x, plus 3, the natural log of the cosine of x, minus 1/2, the natural log of x squared minus 1. So dy dx multiplied by 1 over y will be equal to 8 over x plus 3 over the cosine of x multiplied by the negative sine of x minus 1/2 multiplied by 1 over x squared minus 1 multiplied by 2x. It's not done yet, because remember I have this 1 over y, so I need to multiply both sides by y. Let me move this over. And so I have dy dx, or if you want, f prime of x is going to be equal to my y. My y was x to the 8th cosine cubed of x over the square root of x squared minus 1, and then it's going to be multiplied by 8 over x minus 3 the tangent of x. This 2 and that 2 cancels, leaving me just minus x over x squared minus 1. And that's my final answer. Much easier than trying to use the product and quotient rule and chain rule all in one place. If I look at f, natural log of y is going to be equal to 4. The natural log of the square root of x squared plus 3 minus 5 plus the natural log of 2x minus 1 plus 4 the natural log of x raised to the 2/3 minus x plus 7 minus 2 the natural log of 1 minus 4x minus, and the reason there's not a minus is because this 7x minus 9x squared is in the denominator, the natural log of 7x minus 9x squared. So now I'm ready to do the derivative. So I have 1 over y dy dx is going to be equal to 4 multiplied by the square root of x squared plus 3 minus 5. The derivative of the square root of x squared plus 3 minus 5 is going to be 1/2 x squared plus 3 raised to the negative 1/2 multiplied by 2x. Then my next term, I'm going to have plus 1 over 2x minus 1 multiplied by 2. My next term is going to be 4 multiplied by 1 over x raised to the 2/3 minus x plus 7 multiplied by 2/3 x raised to the negative 1/3 minus 1. And then I'm going to have minus 2 multiplied by 1 over 1 minus 4x multiplied by a negative 4. And then my last term is going to be minus 1 over 7x minus 9x squared multiplied by 7 minus 18x. All right, there is the entire lovely derivative, with exception of I still need to multiply by y. So dy dx will be equal to my original function, which was the square root of x squared plus 3 minus 5 raised to the 4th power, 2x minus 1, x raised to the 2/3 minus x plus 7 raised to the 4th, and then 1 minus 4x, the quantity squared, 7x minus 9x squared, and then this is going to be multiplied by, so I'm going to have 2, let's start with this 2, and that 2 will cancel, so I'll have 4x over the square root of x squared plus 3 multiplied by the square root of x squared plus 3 minus 5. That's my first term. And then I'm going to have plus 2 over 2x minus 1. And then I'm going to have 4. So 4, so plus 4. This is going to be multiplied by 2/3 x raised to the negative 1/3 minus 1 divided by x raised to the 2/3 minus x plus 7. My next one is going to be double negative, so it'll be positive 8. So plus 8, 1 minus 4x. And then my last term is going to be minus 7 minus 18, 7 minus 18x over 7x minus 9x squared. Boom, there it is, in all of its glory. Holy crap, that took a long time. All right, applications. Why do we want to do this? Because there is real life applications. The number of cases of influenza in New York City from the beginning of 1960 to the beginning of 1961 is modeled by this function, 5.3 e raised to the 0.093 t squared minus 0.87 t from 0 to 4 for t, where n of t gives the number of cases in thousands and t is measured in years. T of 0 corresponds to the beginning of 1960. Show work that evaluates n of 0 and n of 4 and describe what these mean. So if we do n of 0, so 5.3 e raised to the 0, this tells me that 5.3 thousand people were infected in 1960. N of 4, since the t represents years, would be 5.3 e raised to the 0.093 multiplied by 4 squared minus 0.87 multiplied by 4. Now, whatever this number is, I don't have a calculator with me. This is the number of thousands of people infected 4 years later. So if this represents the people infected in 1960, 4 years later would be the number of people infected in 1964. Now, the second part is the more interesting part. It show the work that evaluates n prime of 0 and n prime of 3. So the first thing we're going to do is n prime of t. This is 5.3 e raised to the 0.093 t squared minus 0.87 t. Now, the derivative of that exponent is going to be 2 multiplied by 0.093 multiplied by t, and then minus 0.087. So it's the derivative of the exponent. And that tells me when n prime of 0 is equal to 5e raised to the 0, and then we're going to have multiplied by 2 multiplied by 0 minus 0.87. Now, whatever this represents, that should be 5.3. 5.3. Whatever this number is, I don't have my calculator, whatever this number is, that's how many thousands of people were being infected per year in 1960. So this is the thousands of people infected in 1960 per year. Okay? So the n prime of 3 would be the same thing, except for it would be the thousands of people infected in 1963 per year. So remember, because the derivative is the number infected with respect to time, it is the number infected divided by the time unit, in this case, year. So that shows us how quickly they were being infected in 1960 or in 1963. Nice real-life applications, and that's it for this video. Kind of long, but not too bad, and we'll see you in class.